Okay, let's do it. Yeah. The next topic is, well, it's texturing and lighting, basically. So it's some more advanced lighting techniques than what we looked at previously, but they are all related to various ways to use textures to achieve better lighting. And the first one is normal mapping. Like this. It might be nice, but it's not.
Surely gonna help. It actually does. It actually does. There's something. You know what? I actually fixed my laptop once by taking it up, picking it up, and smacking it at the table. Full not this one, but another one. So it was complete broke. It couldn't fucking fix it. I got so angry. I just took it and smashed it at the table, full speed. And I thought it would break. And then it's pushed the button, turned on, and then everything was just as new. I just reset the shit out of it.
So this is just an image I found that that explains what it is. What we can do is that we can use a texture. We can use texturing to put more detail, more lighting detail, surface detail you would call it, on a model. So this texture doesn't actually color the model at all. This is just a result of lighting calculations that we see. You could have, of course, achieved the same by making the model with a lot more polygons. And this is also how this normal map has been done. It's been modeled very high resolution in a modeling program, and then the resolution has been reduced, and a lot of this detail that's in the high resolution model has been converted into normal maps instead.
Looks like sophisticated.
Yeah.
Look at the face. Yeah, but look, it's just the face. It's the same face expression as it has in Get Carter. Yeah, the crooked nose, the uneven mouth.
I think the first time I saw normal maps really used in commercial game was Doom 3, where they sort of pioneered this technique of making really high resolution models in the modeling software and then converting that into nice normal maps. And Doom 3 has a lot of normal mapping in it, both diffuse specular lighting and stuff. In a normal situation, when we are when the GPU is drawing a surface, this is like maybe a triangle seen from the side. Then you have these vertex normals. So there are normal vectors that are defined at each vertex. So you say this surface is like a triangle, so that, of course it has like two vectors, so we can see these two vertices that we can see one at each end, right? And this in between is just a polygon that's drawn. We get a little more detail than that because the rasterizer interpolates these values. So we have them only defined. The hardware only knows these two normal vector values. But in between here, they are interpolated. So at this point here, this is a bit hard actually. I should have probably accelerated it more. So here in the middle, it will get sort of straight up, kind of. These blue ones are the interpolated values. And they just get linearly interpolated across the surface. So the surface, you could say what it actually, the equivalent of it is in terms of the surface is really that the interpolation means that the surface is actually something like this with respect to lighting. It becomes smooth. So it has a smooth transition. The slope of the surface in the local places here, it smoothly transitions from this normal vector to this normal vector. So the blue ones are interpolated normals. Yep. And you can say that it simulates a surface. The surface is not actually there, it's flat. But when the lighting calculation is done, the surface really looks like this. So what we see on the screen makes us think that what we're seeing is the curved version. Simulates this surface. Okay. And this is what we see here. This is why the lighting is very smooth across these. So maybe this guy is maybe a little round, but it could actually be a quite big polygons that we see, because we still get this smooth lighting across it because of this normal interpolation that's happening. So it's a nice illusion. With the normal map, we still have the vertex normals and the smooth surface. But we use a texture to look up in each place, in each sort of across this polygon, we look up across the texture, so we find a lot of different little normals. I call these little normals because I don't think there's any better word for it, but so they can vary a lot like this across the surface because they're looked up in the texture. So they can be something like this. And maybe a little bit like this or something. And this, of course, simulates a surface which is much more complex. It will be maybe like this. Could be. So this purple surface is, of course, not there, but it's just it looks like the surface is like this because of these normals that are used for the lighting calculations. Little normals looked up in normal map. So as I said, the normal map is really just a texture. It's mapped just the way that color textures are mapped using UV coordinates at the vertices. It's really just a texture. But we don't see the texture, don't see the colors of the texture. Instead, it affects this normal calculation in the lighting. Oops, no, that's the right place. No, 9. And yeah, I have another slide about how this happens in a little more detail. So we're going to look at a normal map texture now. Oh, where did I put that? Where did I put that? Just want a normal map, so I guess I could just take it from the slide. There. Yeah. It looks like this. It's easy to see what the contours would be, although this is false color that we see. It really isn't a lighting calculation at all. It's just that the normal map, I mean, textures is of course always images, so we always interpret what is in them as colors, and it also allows us to edit a thing like this with a image editing program. But this is actually something completely different. It's each pixel is a little vector that gives us this shape. The reason it's blue is because usually we map red to X, green to Y, and blue to Z. And if a lot of vectors on a surface would be pointing out at us, like if it's only flat, and that is of course the blue value, so it's 0, 0, 1, and that would be a completely blue, or maybe it's like it's actually usually a half 1, because it's the vector can also point inwards. So that's the light blue color that we see a lot in normal maps. It's simply because this vector is pointing toward the z-axis a lot. And then at the edges you see a different color because the vector is pointing differently than just straight at this case at the camera or the viewer. To achieve this, we pass this, just like a color texture, we pass it to the fragment shader, and it's sampled in the fragment shader. So at each fragment we look up where are we on the normal map, what is the value here. And then, as I said, we need to reinterpret this color into a vector. So the most simple way to do that is just to convert the values. We just say that the color is equal to, the vector is equal to the color. They are just numbers, right? And I did have this here. Oh, that's yeah. This is the text image. And this down here is the rendered result. Again, this floor that looks like it has these cobblestones does not have a color texture. It's just it's colored with a constant color, and it's the lighting calculation that does all this. This is what is known as per fragment lighting calculation, if you stumble across that. So we do the lighting calculation for each fragment. Maybe just an arrow or two. Yeah. So we need to write a little bit of code in the fragment shader to achieve this, and this is what also happens if you use the default Unity, one of those normal mapping shaders. It has the code that does this thing. So much actually. No, sorry, there's one more about normal mapping. Yeah, when doing something like normal mapping, we have another vertex attribute, which is called a tangent. Oh, did I make a mistake there? No. I did, didn't I? We also talk about tangent space sometimes, but I'll get to that. Huh? Oops. So again, we have a normal map texture. This is actually the image we're looking at. It's not a map texture, it's just the image. Like if we open it in Photoshop or something, it would look like this. Oh, I see what I wanted to do now. Just 1 minute. Take the entire thing instead, like this. It's just to repeat what we did. The point with tangents is that we have these little normals that we look up in the normal map. But one problem that we have, for one extra caveat, is that they are not they're not defined in the usual model space of the model. They are defined in something called tangent space, and it's the intuition of it is that you see on this surface here all the blue vectors, they're all pointing out at us, but this texture could actually be wrapped around some object, and it will still look the same. So if it was defined in the model space, then all the little vectors should be transformed into this space. This is not done in the actual map itself, so it's defined in this tangent space, which is like the surface space of the model. And then in the shader, we need to recalculate those vectors into the model space in order to do proper lighting calculations on them. So the orientation of the surfaces and the interpolated normal vectors from the vertices matter. It's too big. Tangent space. So I'm going to illustrate what is this tangent. So let's say we have a point on a surface. First of all, at this point we have a little normal. That's what we always see. Normal. And it's actually defining sort of the two other vectors to have a proper coordinate system basis. That's what the tangent space is. So the normals is just one vector that gives us a direction, but it doesn't give us complete information about the orientation of the surface here. So we put in another vertex attribute, which is the tangent. A tangent means something that is has the same slope as something else. So it's, and then for the third one, we have something called it's called the binormal. It's just a strange word. Binormal. Okay. So imagine that, I mean, when we the geometry that we get from modeling software or whatever, that already contains normal vectors that defines the slope of the surface. So at every vertex there is a normal vector that says which way is the surface sloped in this position here. When we want to do something like this, then we also want tangents. So just like the normal is defined for every vertex, there is a tangent for every vertex, and it should it should be defined like this. So it also tells us something about the slope of the surface, but gives us more directionality. And the binormal actually also should be defined, but that can easily be calculated using these two, so we don't need it in the data. It's usually not put in the data. We just calculate it in the shader, and we use a cross product to because we know that these are unit vectors and they are perpendicular. So if we take the cross product of those, then we get a third vector that is perpendicular to both of these, and we do that to calculate the binormal usually. So, but remember now that that to do this, we have another attribute on the geometry, which is these tangents. So what we use this for is that we use this as a basis. So if you have a vector like 3 values, a vector, then you can interpret that in this basis. So the basis is pointing somewhere, and if we use this basis to interpret it, then it's like this was the coordinate system of the vector. That's what the basis mean. And the math to do that is a linear combination. I'm going to put the equation little normal. We want to calculate that properly. And we take these values x, y, z from up above that we look up in the map, and we simply multiply the x value with the tangent, and multiply the I value by the binormal, and the z value by the normal. So that's the additional calculation that we have to do in a normal mapping shader to have everything work properly. Because this is not defined in model space, it's defined in this tangent space, which is coincident with the surface of the model and not the model space itself. Put another note on this, which I'll put here also. Tangent. That is a vertex attribute, just like normals. Okay. So much about normal mapping. A lot of stuff, but we are going to work with normal mapping shader, so that's why I put a little more effort into this. I'm going to talk a little more briefly now about 2 other techniques that are mentioned in the study plan, and they are very sort of normal, commonplace kinds of texture lighting, advanced lighting. And they are environment mapping, reflection mapping is also called, and shadow mapping. So, environment mapping, aka reflection mapping, or sometimes also called cube mapping. Also, that's a special case, but it's the way that's we normally do environment mapping. I have, as usual, a little example of what this is used for. This one. Yeah, these car games like Gran Turismo or something has a lot of environment mapping in them. So what this does is it makes more realistic specular highlights on stuff. So the way that this car has this shiny reflective surface that acts a bit like a mirror, so you can actually see the surroundings reflected in this. And when it's nice for a car game because the car is moving, so you can see the environment is moving and the reflection of. That's why it's used a lot. It makes it very realistic. a big one. Yeah. I thought about doing a little trick here. So maybe just, oops, black. Make a little drawing of this car for the illustration. Yeah. Okay.
Well, it kind of looks like a car. I wouldn't drive it.
I gotta get that tattoo.
I wouldn't drive with the rear tire like that, but
So the reason we normally call it cube map is this cube is actually a cube of textures that we define around the object. I'm not going to draw the sixth side. Well, it is there, you could say. So we sort of surround the object by these six usually square textures, and that is what is called a cube map. The idea is to render the scene, to like put a virtual camera at the point of reflection, and then draw what the scene looks like without this object in it, because then we can sample that, we can calculate the reflection of each point, and then we can reflect that somewhere on the cube, and then we can see what would we actually see in this direction with the mirror that's on the hood here, and that is specular lighting. Of course, it's the perfect reflection, right? So I'm going to illustrate that. So here we have the camera, and we are looking at a certain, like, how do we draw this fragment situation, and this is the normal vector. We need to have that, and the reason we need that is because what we want to do is to calculate what is the perfect reflection in this point. So we start at the camera and then trace a vector to this point, and then we use a calculation similar to what we saw in the slide about specular lighting to do a perfect reflection. So we want to have a vector that goes in, like, what we call the opposite direction, and that's just reflecting this vector around the normal vector. So the angle to the surface is the same, but the direction is opposite. And then now we know where to sample the normal map, or the cube map, we can call it, not normal map. Oops. And I need a comment also about what I said about the cube map. 6 textures with rendered environment seen from the point of view of the model. Just to repeat what happens, we have the scene. In order to get this cube map, we actually put the camera right here, and then we sort of film what we see, the rest of the scene, in these 6 directions, and we render the result, and then we take those results from the frame buffer and convert them into textures, which we then use to make this lookup so we can see what would be reflected. Of course, that would be pretty expensive to do if we would have to do it separately for each fragment. Like now, this point is a slightly different place, so in theory, we have to do the same again to render these 6 again, because they would change a little bit. And of course, you never do that, because that would be crazy expensive. So, for instance, what these car games do usually is that they do one cube map for the car. Like they take a center point of the car, put the camera there, and then they render a nice cube map. But they probably do one each for every car, because they want the effect to be pretty realistic. Other games have static cube maps. That's a lot more common. These games chose that because it uses it in a dynamic way. But many times you have just a static cube map which never changes, and it's just pre-rendered. It's done offline, and it's used, and that can be good enough for many effects. But it won't give you this effect of the environment rushing by on the car's hood. So that's why they do it dynamically in these games. Yep. Shadow mapping. Which is also very, very common in like games and other real-time graphics applications. So we're going to talk a little bit about them, how they work. I'm going to have an image that we use. I mean, this is the effect that we're after. We want to have nice shadows that are dynamic and that sort of climb up on the walls and stuff like that. So they are realistic. And of course, you can see this a character that probably moves a lot and changes shape and stuff. And the shadow, of course, should correspond to that. So it needs to be calculated in real time. So how do we do that? Well, with shadow mapping, I think this illustrates the technique pretty well. The idea is to, again, like we did in environment mapping, we do sort of an offline rendering of something else. So we take the camera and put it at the light source. So we render this rabbit from the point of view of the light source, and in black probably. And then the resulting image is converted into a texture, and this texture is then mapped onto the environment using a projective transform. That's basically the technique. So do a little illustration of that. Okay.
Well, I'm getting better, huh?
Am I?
It almost looks like a bunny.
Sort of. Tracing is good because it means that someone that absolutely cannot draw can still do something. Okay, I put the light source, and we put the shadow map texture. Put this behind. There. I thought about actually putting this shadow in the picture as well. Yeah. Yeah. So we have this projection that goes on from the light source like this. So the drawing part is, yeah, we put the camera here and we draw what we see using just black. And this becomes this texture then, and this texture is then mapped onto background geometry using a perspective transform. It's the same transform that we use to make view, to make the view part of the transform. But it's from the point of view of the light source. Yeah. I think there is a shadow mapping module in Unity with these soft shadows, I think they call them. And that's because shadow mapping, there are other ways to do shadows. Shadow mapping is quite common in games. I mean, these Unreal Engine powered games, a lot of them have shadow mapped based shadows that you can see, and they have this advantage that it's easy to make soft shadows that have these soft edges, which shadows in real life often have, because I mean, very simply you can just blur this texture when you're drawing. You can apply some blurring to it, and that will actually give the shadows these soft edges. The other most common technique is stencil shadows. I'm not going to talk about that a lot. There's no slide about that. That's actually also pioneered in this Doom 3 originally, in a real-time game. And you also see those a lot, especially in games that are powered by id Software engines, like Call of Duty and so on. They have other properties than shadow mapping. They are nicer in some ways, but they are always very sharp. Stencil shadows it's difficult to make soft shadows with stencil shadow technique. And these, for instance, these Call of Duty games often have outdoor scenes, so the lighting is the sun. And the sun, if it's bright sun, then it makes a very sharp shadow, so that's very nice. It's a very small light source that has no extent. But it's not very good for indoor scenes with lights that have big area, because they would produce very sort of soft shadows like I do here, and their stencil shadows is not very good. So usually you use shadow mapping instead. Okay,